Hello everyone, my name is Stuart Mitchell. I'm a graduate math student who works for Professor Oakes, and I will be going through your video lectures for Math 70. In the first one, we're going to be talking about a few different topics, namely in the first two. We're talking about different types of numbers. So here and here, we're talking about different kinds of numbers. In 3, 4, 5, and 6, let me pick a different color for those. In 3, 4, 5, and 6, we're talking about comparing numbers and ordering them from least to greatest. And then in 7 and 8, we are converting fractions to decimals. Okay, so for our first topic here, which I'll switch back to green for that one, since we were working in before, we're talking about different types of numbers. So for both of these questions, it might be helpful to consider just a breakdown of the types of real numbers, because more likely than not, you'll be working in mostly real numbers for all of the math that you have to take. So overall, we have the real numbers. Those include like all of the numbers or types of numbers you're familiar with. And then from here, we can break it into two sections. We have irrational numbers. And then we also have rational numbers. Irrational numbers are numbers that generally are decimals that or have decimals that go on forever, and they don't have any kind of pattern. They just kind of go on and on and on and never stop. So those are irrational numbers. Those would be never-ending decimals. That would be numbers that go on forever. That'd be like square roots, like the square root of 2, square root of 6, pretty much any square root that's not a perfect square already will fall in this category. And irrational numbers, just because like they go on forever, they don't generally have any repeating qualities, or just like a decimal that's like 1.34645 and just goes on in a random fashion forever. That'd be irrational numbers. And you can't do a ton. I mean, they're important, but like they're the ones that don't have any kind of pattern, they just go on forever. Rational numbers, on the other hand, do have a pattern. We'll separate these two because we don't need them to get in each other's way. Rational numbers, on the other hand, are numbers like all fractions. Such as 2/7, all proper fractions, 2/7, 3/4, 7/9, -1/5, and so on. It can be positive and negative. An important thing to note in this rational numbers section is that generally, if you're talking about decimals, they're decimals that have a terminating place, like -4.276 or like 0.45. Numbers that don't go on forever, or the decimal place doesn't go on forever, it usually ends. An exception to make, though, not necessarily an exception, but just it's important to note, some fractions result in decimals that go on forever. But it's in a digit that repeats. For example, 1/3 in decimal form is equal to 0.333 it just 0.3 and it goes on forever. And we denote that as 0.3 repeating. So it goes on forever. So that would take care of that there. And then inside of the rational numbers, those are done. The rational numbers don't really have anything else inside of them. Inside of the rational numbers, actually, I'll pick a different color for that one. Instead of green, we'll pick purple. Go with that. Inside of inside of rational numbers, inside of reals, we have numbers that can be expressed as positive and negative, that can be expressed as fractions over 1, like -3 over 1, -2 over 1. And so on. You get the idea. These are all called integers. The ones in purple, integers. Because as you know, anything divided by 1 is just itself. But that's how they can be expressed in terms of a fraction, which are typically how rationals are thought of are as fractions. So in this sense, here we have we just have like all the positive and negative numbers. This goes on in the other direction forever too, of fractions that can be expressed with the denominator of 1. Those are called integers. Positive and negative whole numbers, or as if you want to think of it that way. And then within the integers, within rationals, within reals, I have to scroll down just a little bit first. Within all of this, we have just the whole number, or just positive whole numbers, which doesn't include 0 either. 0 isn't necessarily considered positive or negative, but it's not positive. We just have 1, 2, 3, 4, and so on. Those are called, oops, sorry, hold on, that went a little haywire there. I don't know why it doesn't want to go in a circle. Are called counting numbers or natural numbers, which again are just positive integers, just the positive integers or positive whole numbers. So that is basically how the real number system is broken down naturally. You go from, if you want to think about it from bottom to top, in kind of a sequential order, you start with your counting numbers. And then when you add 0 and the negative whole numbers, you end up with the set of integers. And then if you add fractions, which also result in decimals, because you can change fractions to decimals, though that results in rational numbers. And then when you add the irrational numbers, which are the decimals that don't end or don't terminate or just go on forever in a random sense without any kind of pattern, you end up with the whole real number system. So that's all of the real number system. So if we apply what we just talked about to this question now, which of the following is an integer? Well, if we use what we just saw, as in the example here, this is a fraction which falls under rational numbers. So this couldn't be it. If we talk about -15.99, that qualifies as a terminating decimal, as we see down here. It's a terminating decimal. So that can't be it. And then the square root of 6 would be an irrational number because it's not a perfect square. 6 is not a perfect square. So when you take the square root of 6, you're going to get just some long decimal that goes on forever. and doesn't repeat or make a whole bunch of sense. Doesn't have a pattern, I should say. So the only thing that's left, and as we saw further below, this -4 would be the only integer because it can be expressed as a fraction over 1. It's a whole number. It's a negative whole number, so that'd be considered an integer just by definition. So -4. Okay, perfect. And now piggybacking off of that, true or false? 0.45 is a rational number. Well, as we just saw here, and in this example as well, it's a terminating decimal, has a finite number of places after the decimal point, and it could be expressed as a fraction. It could, if you wanted to think about 0.45 a different way, it could be expressed as 45 over 100. And then if you simplified that, you could divide by 5, and then you'd end up with 9/20. So it falls under fractions, so it is a rational number. That's what a rational number is a fraction overall. So this one is true. Okay. So moving right along, in 3, 4, 5, and 6, we're talking about the ordering numbers from least to greatest. So I will go down here for that a little bit. Okay. Okay, so when we're talking about ordering numbers from least to greatest, you always want to think about reading it from left to right. This means greater than. This means less than. And the typical convention that's always used is that the point is always going towards, sorry, my stylus is freaking out a little bit over here. It always points towards the smaller number. So, or if you want to think about it too, I don't know if you're taught this in elementary school, but sometimes I still think about this, even in graduate school, as silly as that may sound. If you think about the inequality symbol, the greater than or less than, as like the open side being like an alligator mouth, you always want the alligator mouth to be eating the bigger number because you'd always want to eat a bigger portion. So you could think about it that way too, if that helps. That's what I do, as silly as that sounds, but you know, it happens sometimes like that. So now we're going to explore these true or false, keeping in mind too that when you see a negative number, the larger the magnitude of the negative number, like the bigger the number attached to the negative sign, the smaller it is because it's further away from 0 on the other side of 0. So it sounds a little counterintuitive, but you'll see what I mean when we're talking about as we go through these examples. Okay, so in this one, true or false, -8 is greater than 0. Well, we know that -8 falls to the left of 0. In other words, it comes before 0, so it would be less than 0. So this is false because we would have had to go in the other direction. Next one, true or false, -25 is less than -35. Okay, so this one is one where you'd want to be careful when you're comparing two negatives, because upon first glance you may think, oh yeah, this is right because 25 is less than 35, but be careful, pay attention to the negatives, because -35, although positive 35 is larger than positive 25, -35 is further away from 0. It comes before -25. It's further away from 0. So -35 is actually smaller. This one is the smaller number, so this would be false. Okay, so Next, true or false, 7/9 is less than 2/3. In this sense, or in this instance, we are comparing two fractions. And we're comparing two fractions with unlike denominators, which is a problem because we can't really say anything about those for sure. So let's consider these down here and see what we can do to compare the two numbers together. Okay. So if we think 7/9 is less than 2/3, that's the statement we are given. Well, in order to adequately compare these, we're going to need a common denominator, which means we need to make the denominators the same. Luckily for us here, 9 is multiple of 3. So we can multiply 3 by another number to get to 9. So we don't have to do anything to this fraction. We just have, or to this fraction right here, we just have to do something to this one. And it's important to note, whatever you do to the numerator or denominator, like, you have to also do to the opposite side. So like, we have to multiply the denominator by 3 to get it to be 9, but then we also have to multiply the numerator by 3 so that the whole fraction doesn't change, so it remains equivalent. And this is equal to 6/9. So our new expression that we're comparing becomes 7/9 is less than 6/9. And now, when we're comparing these, we're looking for the larger numerator. Since these are both positive numbers, a larger numerator is going to lead to a larger number overall. So this one, 6/9, is actually the smaller number. So this is false, because 7/9 is greater than 6/9, or 2/3, as it is reduced, or as it was when it was reduced. So that one is also false. Okay, and then moving along, the next one, we have that -1/10 is greater than -9/10. What's nice for us here is that these already have common denominators, so you don't have to worry about finding one. Although the trick here is that these are both negatives, and we have to consider what we considered all the way back up in number 4 here, is that the larger the magnitude of the negative number, the smaller it is. So this -9 in the numerator here is actually smaller than the -1, because it would come before. So -9/10 is indeed less than -1/10, or -1/10 is greater than -9/10. So this statement is true. Okay. Bear with me just for a moment, because I'm sorry, that was the wrong button to hit. I need to erase some things to make some more room for the last section. I'm going to erase this first one since we already covered it. We don't really need it anymore. Okay, and now we are going to talk about in blue. I'm just going to make it light blue in case they go off the edge, and I want to make sure we can still see what's going on. For 7 and 8, we are talking about fractions to decimals. So let's consider the first one, 7/9. This is the same thing as saying 7 divided by 9. So that's exactly what we're going to do. We're going to divide 7 by 9. Now this is probably different than than the division you've seen before, like normal division. Sorry, bear with me. My computer hates me sometimes. Oh my goodness. There we go. That's what I wanted. Okay. this is a little bit different than normal division just because we are dividing a smaller number by a larger number, which generally is not something that you would do, but we can. It is possible. I promise. I wouldn't lie to you. It'll work out. So we are going to put the 7 under the division house and the 9 on the outside. Obviously, we can't have 7 go into 9. It'd go in 0 times. So make note of where the decimal sits and put it on the roof. Ooh, in the right place. Goodness gracious. Sometimes this does not work. There. Okay. So we make note of where the decimal is. We put it in the right place up there. And then we can add a 0 because that doesn't change the value of 7 at all. You're just adding you're adding a 0. But then we can think of this as 9 going into 70. And we know that 9 goes into 70 7 times. 7 times 9 is 63. When you subtract, you get 7. And we're in the same predicament again. 9 can't go into 7, so we have to add another 0 so that we can carry it down. So we have 9 going into 70 again, which, as you can see, goes in 7 times. This would be 63 again. When you subtract, you get 7. And hopefully now you can start to see a pattern. Every single time that you do this, you're going to have to add another 0, bring it down, and consider 9 going into 70. So you're going to end up with a bunch of 7s that go on forever. A way to express this would be to say that this equals 0.7 with a bar on top, which means repeating. That just means the 7 will repeat itself forever. It's also important to consider here in this situation that if you did 7/9 or 7 divided by 9 on a calculator, it would approximate it to 0.7777, however many spaces it has to display, and then it would round off to an 8 at the last decimal place. That's not wholly accurate. It just does that because it ran out of room, and this goes on forever, but this just stands for a bunch more 7s in a row. It just rounds it up to an 8. But it's important to consider that, to take note, because if you did it on a calculator, you wouldn't get the completely right answer unless you had some kind of insight beforehand. So it's just important to keep that in mind as you're moving forward. Okay, and then we have one more example left. We have the writing 3/8 as a decimal, which is really similar to what we just did. It's the exact same process, although this one will end up just a little bit nicer because it behaves a little bit better than this the first one does, which is always nice. Okay, so finally we have 3/8. Same thing. You can think of this as 3 divided by 8. So 3 goes in the division house, 8 goes up here, or 8 goes outside. 8 can't go into 3, it goes in 0 times, so make note of where that decimal point sits. And then add a 0, as we did before. So now we're considering 8 going into 30. Well, we know that 8 can go into 30 3 times. 3 times 8 is 24. When you subtract that, you get 6, but 8 can't go into 6, so you have to add another 0, carry it down. Now 8 can go into 60, we know 7 times, and 7 times 8 is 56. When you subtract, you get 4, but 8 can't go into 4, so you have to add one more 0 for now. And then we know that 8 goes into 40 exactly 5 times. So we don't get any remainder. And so you get a decimal that terminates, which is nice. You get 0.375, which is 3 divided by 8. And that is how you convert convert fractions into decimals. You just divide them how they're stated. 3 divided by 8, 7 divided by 9, whatever two numbers you have. And that would conclude the first lecture. Thank you.